Alright, AP Chemistry, this is Chapter 11, Colligative Properties, and there's technically 3 colligative properties. Every once in a while they throw vapor pressure in as a colligative property. Sometimes it's included, sometimes it's not. Colligative properties depend on the concentration of the solution, not on what dissolves in it. BPE, FPD, OP, and VP. And just a quick comment about them. What happens to the boiling point of a pure solvent if you put a solute in it? Raises it, elevation. What happens to the freezing point of a pure solvent if you put a solute in it? Depression, lowers it, etc. The other thing we're going to discuss, the Van Hoft factor, that'll be the end. Alright, so what are colligative properties? Colligative properties depend on the concentration of the solution, not what dissolves in it. Normal boiling point of a pure solvent, a normal boiling point of anything, the temperature at which the vapor pressure of the solution is equal to the atmospheric pressure. Right now, so think about it for a moment. Boiling point of water is when the vapor pressure above the liquid water is equal to the atmospheric pressure. A non-volatile solute elevates the boiling point of solvent. Please remember, a non-volatile solute will include solids, both molecular and ionic. Formula to calculate the change in temperature from the pure solvent's boiling point to the solution's boiling point is Kb, molality of the solute. The Kb is a constant that will depend on the solvent, not the solute. It is a constant that's listed on page 517. It's also a constant that's got to be given to you. Most of the time our solvent's going to be water, so you're going to be using the same Kb and Kf when we get to freezing point depression. So the Kb's are constant. So now you have a variable that was 3 variables, now it's whittled down to 2 because one of them is a constant. Molality of the solute, you're familiar with. We did this at the beginning of the chapter. Molality is a concentration of a solution. It is calculated moles of solute per kilogram of solvent, and it's used because mass does not change with temperature. Volume changes with temperature because, of course, volume, the liquid phase, evaporates into the gas phase, so you lose liquid. When you increase temperature, you don't lose mass. Molarity is moles of solute per liter of solution. Molality is moles of solute per kilogram solvent. One of them is all mass, the other one is dependent on the volume of the solution. Normal freezing point, the temperature at which the vapor pressures of the solid and the liquid are the same. Non-volatile solute depresses the freezing point of the solvent, and it also has a 3-variable equation. It also has a constant that's dependent on the solvent, and most of the time that solvent's going to be water. And it also uses molality instead of molarity because molality is mass dependent, molarity is volume dependent. Molarity changes with temperature change. Alright, here's this pretty little phase diagram for water. Let's see, notice that if you have the black line is pure water, the blue line is water and a solute, and this difference here from the black line to the blue is a depression, and this is freezing point depression, so it's the change in temperature from the freezing point of pure water, which is 0 degrees Celsius. Put a solute in it and it lowers it. That's why they use salt on ice. Over here the black line is, of course, the boiling point of pure water, and the blue line represents pure water and a solute. A solute will elevate the boiling point of water. Let's see, what else? Solid phase, liquid phase, gas phase, and again the blue line is your solution, so it's pure water with a solute in it. This guy right here is the triple point of the solvent, and the solvent is, of course, water. At that spot right there, all three states of water are present: the solid, the liquid, and the gas. Ice, the melting point of ice will decrease as the external pressure increases because the density of ice is less than liquid. And the rate of ice melting is equal to the rate of water freezing. One's melting, one's freezing, but they're basically doing the same thing. They are changing from one state of matter to another. The boiling of water will depend on the external pressure. So the boiling of water depends on external pressure. Alright, so here's an example: 15.3 grams of sodium chloride placed in 20 grams of water. Notice mass. I see solute, solvent. What are the freezing point and boiling point of this solution? Alright, now a couple of things I want you to realize. They're not asking you for the change in temperature. Grant you have to calculate the change in temperature, but then you have to figure out what the new temperature is. Okay, so I calculated the new temperature for the freezing point of a solution of water and salt, and I calculated the new temperature for the boiling of water and salt. And a couple of things I want you to know. It's molality, because molality is all mass based, all dependent on mass. The freezing point of pure water is 0 degrees Celsius, so the new temperature is lower than 0 degrees Celsius, so it's a negative number. The boiling point of pure water is, of course, 100 degrees Celsius, so the new boiling point of the salt solution is going to be greater than 100. So a couple of things to remember there. Now here's the kicker, here's the little twist. Okay, Mrs. G, great, I can plug in problems. Works for me, I can plug the numbers in and do the math. What the heck is that? Well, if you remember the example we did for vapor pressure, and the concept that ionic salts alter all these properties more than molecular, take a look at the ionic salt. That's a soluble salt. There is no sodium chloride in water. There's sodium ions and chloride ions. All right, so in other words, the sodium chloride, since it's a soluble salt and there are two ions in there, it's going to double the effect. So you got to watch out for ionic compounds, just like vapor pressure. Another example. This one's a little different though. We can use freezing point depression and boiling point elevation to either calculate the mass of the solute or molar mass of the solute. Alright, so here's our example. what we're looking for is the mass of ethylene glycol in the solution. So what I did first was I wrote down everything I had. Notice that ethylene glycol is not an ionic salt, it is a molecular compound. So we don't have to worry about it affecting the temperature change like an ionic compound does. I don't have to double it or triple it or anything like that. So ethylene glycol in water, they give me the solvent water, they give me the mass of the solvent water. 10 liters is 10 kilograms because of the density of water. They give me the new freezing point for the solution so that your car's radiator doesn't freeze up. And it's a negative 23.3. So they want a solution, or they have a solution that will freeze at negative 23.3 degrees Celsius. Change in temperature for freezing point, Kf times m. M is my unknown. Why? Because K is a constant, and they gave me the change in temperature. So the molality of the solution has to be a particular molality in order to change the freezing point to negative 23.3. That molality has to be 12.5 moles of ethylene glycol for every 1 kilogram of water. Well, I have 10 kilograms of water, so how many moles of ethylene glycol do I need to put in my 10 kilograms of water to get 12.5 moles per every 1 kilogram? That's 125 moles of ethylene glycol I'm going to need in order to make the proper solution to freeze at a negative 23.3 degrees Celsius. Well, 125 moles is really hard to mass out, so I multiply that by the molar mass of ethylene glycol. In order to make a solution with a concentration of 12.5 moles for every 1 kilogram of water, I will need 7.76 kilograms of ethylene glycol. Then I will get a freezing point of a negative 23.3 degrees Celsius.